Hello everyone, my name is Aditya Khandelwal and today I'll be talking about our work 3D nanoprinted gold microelectrode arrays on flexible substrates, the Gold CMU array. So first, let's start with what are brain-computer interfaces. Brain-computer interfaces are systems that directly link neural activities to an external device, enabling communication, control, or therapy by decoding brain signals. The three main application buckets can be thought of as medical therapies, assistive communication, and human-machine interaction. Traditionally, silicon-based electrode arrays like the Utah array face two big challenges. First, limited electrode density because of rigid fabrication constraints of the semiconductor fabrication processes. Second, limited design flexibility, meaning electrodes can't be customized for different brain regions. With gold nanoprinting, we solve critical issue. First, we eliminate the cytotoxicity risk from accidental silver exposure in the older iteration of the CMU arrays. Second, gold offers excellent biocompatibility while retaining good electrical performance. Bi-flexible substrate. Rigid implants like silicon probes cause tissue damage because they mechanically mismatch with the soft brain tissue. By printing electrodes on a flexible captain substrate, our devices conform to neural surface and reduce the chance of injury and improve the long-term recording stability. In this talk, I'll cover device fabrication, device fabrication and design, mechanical and electrical characterization, the results, and we'll talk about the future works. So first, let's start by the fabrication process, which is aerosol jet 3D printing process. First, the ink is aerosolized by the ultrasonicator. The ink is loaded with nanoparticles of choice. In our case, we use 2 to 3 nanometer loaded gold nanoparticles. The ink is carried to the deposition head using carrier N2 gas, which is then deposited on the XY stage. The XY stage is temperature controlled so that we can control the temperature of the process. As the ink deposits, it solidifies and turns into a 3D structure. In this video, you can see the deposition of printing. So after printing of the probes, we functionalize it by coating it with phosphorescency, which offers the biocompatibility to the probe, and to lower the impedance and improve signal fidelity, we electrodeposit P.PSS. Finally, we expose the electrode tips using argon plasma film. This exposure is done to expose the electrical conductive gold core, which will be able to harness the signals. On the left, you can see the fabricated probes. These are the silver tracks which are covered with polyamide, as you can see in this cross-section SEM image. The polyamide is used to electrically isolate the tracks so that the cross-conduction of signal won't happen. The track pads are made wider so that they can be easily connected with an external device. In this image, you can see the fabricated electrode probes. On the image on the right, you can see the flexibility demonstrated in a fabricated device. So you can see there is no lamination of the tracks or the gold probes, which basically ensures that the device is flexible. Now we talk about the electrochemical impedance spectroscopy of the device. P.PSS reduced electrode impedance by 88%, a dramatic improvement in signal quality, even after repeated insertions in phantom brain tissue, which is the agarose tissue. The electrodes maintain stable impedance, showing strong mechanical durability. This is the electrophysiological recording setup. On the left, you can see a schematic of a rat, and on the right, you can see the surgery in which the implant was placed. In the figure C, you can see an illustrative example of how the signal conduction will happen from neurons, and we will use a device, offline sorter software, to sort the signals gained into action potentials. The recording result is shown in this figure. You can see over time versus amplitude graph in which the heel brace stimulus is given. Heel brace is an external stimulus given which invokes clear neural responses in these places. In these results, on the left, you can see the raster plots, and on the right, you can see the sorted signals. The black lines represent the stimuli provided, that is the heel brace. The gray line represents no stimulation provided. The sorted potential with the mean and standard deviation corresponds to the corresponding neurons. 1 and 2 are different channels through which the signals are obtained. So in conclusion, we showcase the successful fabrication of 3D gold multi-electrode arrays. The P.PSS coating lowered the impedance by 88%, ensuring high signal fidelity. Electrodes showed mechanical robustness through repeated insertion. In vivo tests confirmed clear neural recording responsive to external stimuli. Overall, the Gold CMU array is a promising candidate for clinical brain-computer interface applications. So looking ahead, the big question is, can we record reliable neural signals from freshly resected human brain tissue? This is our next step towards translational and clinical applications.